This is lecture number 16 of the course AU 203 Statistics and Quality Control. We already have started discrete distributions. We have completed so far the binomial distribution and the hypergeometric distributions. Today we will go into a distribution called Poisson distributions. Before going into the Poisson distributions, we will look into the variable, random variable, what we call it a Poisson random variable. Just like the same as in binomial distributions, we have to find out the attributes of a binomial random variable. The same as here, we need to look into the attributes of the Poisson random variable. And then there is a process called Poisson process. So we will do the conceptual understanding of this Poisson process, and then we will derive the probability mass function of a Poisson distribution using the binomial distribution, which is already available to us. And in the end, we will solve the problems related with Poisson distribution. So, okay, let's take an example. Let's say you are a traffic engineer and you are standing at a particular location or intersection, and what you observe is in an hour or in any interval, what you are observing that how many cars actually have passed through that particular point. So this number could be any number. For example, if it is a busy intersection, then could be 100 cars passing in an hour, or it could be 70 cars, it could be 60 cars. So any number can come in. So that number would be a random variable. So just designated, let x is the number of cars passing in an hour, and this number x can take a value 70, it can take a value 60, it can take, if it is not a busy intersection, it could be only 5 cars, or it could be only 10 cars in an hour interval. And if the interval is large, let's say the whole day, then it would be a large number of cars. So we call a Poisson random variable is actually the count of the number of occurrences of an event in a given unit of time or distance or area or volume. So if it is in terms of time, then we call it a temporal domain. If it is in terms of distance, area or volume, we call it a spatial domain. So this Poisson random variable, we are interested in the number of occurrences of an event. For example, in the previous problem, for as a traffic engineer, the number of the event is passing the cars, and the number of occurrences would be called as a Poisson random variable. Okay, what are the criteria which this random variable must meet is it has two attributes. So every Poisson random variable must follow these two characteristics. The first is exactly the same as our events are independent. So the number of occurrences are independent. For example, it could be 60 cars, it could be 70 cars, but if event in a given interval, if it is 60 cars, it has nothing to do with what has happened earlier or what will happen afterwards. So in this way, we can say the number of cars that is passing through the intersections would be considered as independent. So this is exactly the same condition as for a binomial random variable as well. So events occurring should be independent. Second is the average rate of occurrence should be constant. So the probability that an event occurs in a given length of time or given space does not change. So it means if this average rate is nearly constant, obviously it could be constant in a sense of average. So if average rate, for example, on Saturday at a particular time, at a particular intersection, if it is 70 cars, so it could be 73 cars, or it could be 64 cars on a next day, it could be 80 cars or 100 cars, so near about. It cannot be 2000 cars in that particular time passing through that interval. So we call that rate of occurrence is constant. So if any random variable A random variable, obviously we know it should have a characteristic of a random variable, and we have already gone into the definition of random variable quite in detail. So this variable, Poisson random variable, should also possesses the condition of a random variable, and along with it must satisfy these two conditions. So instead of binomial random variable, we have meeting four conditions, because outcome either could be success or could be a failure, and the probability of an outcome should be constant, and the number of trials should be finite. So here we are only dealing with the two conditions. So whenever you have come across with a random variable which is meeting these two conditions, can be considered as a Poisson random variable. Okay, there's some situations in which you are expected to find Poisson random variable. For example, when events occur randomly in an interval or a region. So once you have such a situation, you expect your variable to be a Poisson random variable. Or when your random variable is about the number of counts of that event. So if you are counting it 5 times, 7 times, 20 times, then it could be a Poisson random variable situation. Or usually when your events are not something which is actually rare, so the occurrence is constant, and the rate of occurrence is constant, as well as once you have a situation like events which are rare, which never happens. So the in this usually, I mean, it's not always, but usually once you are dealing with rare events. So from the examples, we will see it later. We will see whether it is a random variable or not. So, okay, let's check out the number of chocolate chips in a cookie. So, once you sprinkle chocolate chips in a cookie, so maybe one cookie might have 5 chips, chocolate chips, another could be 4, or another could be 7. So, here the number of, in every trial, the events are independent, so it is satisfying the first condition. And second is the rate of occurrence, average rate of occurrence is constant. So it cannot have 1000 chips in a cookie, or 500 or 700 chips in a cookie. So this number would be nearly the rate of occurrence is constant. So the number of chips in a cookie would be a random variable, and we can call it a Poisson random variable. Okay, another example, number of deaths from horse kicks in army in a year. So, for example, the army people manages horse, and it is very rarely you will find that a person dies through a horse kick. So it could be either a 0 number in a year, or it could be a 1 number in a year. So such events would also be called as Poisson random variable, because they are independent. And for example, on one particular year, what has happened on the previous year, it has no dependence, so it is independent, and at the rate of occurrence is not changing. Average rate of occurrence is constant. So and this is the situation where events could be considered as a rare events. So such a random variable with number of dash from horse kicks can be considered as a Poisson random variable. Okay, number of times customer is calling a help center in a day. So, and there is always a helpline available for an organization, and customers are calling to the helpline. So the number of times customer is calling, so number of calls received by an organization on the help center could be a random variable, and it is independent, as well as the average rate of occurrence is constant. So if it is not constant, then it won't be considered as a Poisson random variable. If it is constant, meeting these two conditions, then it would be called as a Poisson random variable. The number of particular trees in an acre of land. Let's say you are observing through an aerial view the per acre of a land, how many trees you will find for a particular plant, let's say apple. So you will just count the number of plants. So on an acre land, if you observe, the number of plants could be 400, or it could be 450 or it could be 350. So for every acre of land, if you observe, the number would be independent, as well as the average rate of occurrence from different area of the land, every acre of the land would be constant. So once it is meeting these two conditions, it can be considered as a Poisson random variable. So once you look into the situation, you always need to look whether that variable is a Poisson random variable. If it is meeting these two conditions, then it would be considered as a Poisson random variable. Let's say the number of chips that fail in the first day of an operation. So you have some manufacturing operation, and you are producing chips, and in the whole day, the number of chips that fail on the first day of an operation, so that could be considered as independent, as well as average rate of occurrence is constant, so it would be called as Poisson random variable. Okay, let's say the count of the number of victims of specific diseases. So if this number is independent, for example, trial to trial, and second, the average number of occurrences for is not changing, it constant. Whether you are getting 40, you are getting 50, but you cannot get 4,000 cases of victims of a specific disease, then such a variable would not be called as random variable. If it is constant and meeting these two conditions, it would be called as Poisson random variable. Okay, you are observing a meter length of a material. Let's say it could be a rolling sheet, and every meter it could be sometimes you might 4 defects, sometimes you might 5 defects or 3 defects. So the number of defects or flaws you find in a meter length of a material, that can be considered as a Poisson random variable. You type something, let's say a page or a paragraph, and how many number of misprints you will find on a piece of a page. This is a rare event. It could be 0 misprint, it could be 1 misprint, it could be 2. So you cannot get 100 misprints in a page or something like that. So such a variable could be considered as a Poisson random variable. Okay, so now you need to understand what is actually the Poisson process. So, for example, you have dots, and let's say every individual dot is representing an event, and these events are filled, randomly filled in the space. So what we see is, we take it a trial. Let's say we randomly select a given area, unit area. So for example, I randomly select an area, and represented by this blue dashed line. So how many events I come across in that area? 3 events. So this represents 3 dots representing 3 events. Let's say I take randomly another unit area. This time I came across with only 1 dot or 1 event. Or if I am taking this area, then here I got it 4 dots. So if I randomly select any area, this time I got 5 dots. So this would be considered as a number of events you get in a particular unit area. This is a variable. This could take any number. It could take 1, it could take 3, 2, 4, 5. It can take any variable. So number of events in that space would be considered as a random process. Let's say you have this situation in which every dot is representing an event, and which is randomly filling the space, and you are selecting a unit area. So randomly selecting a unit area. This time you got a 1 event, and second time you got another 1 event. This time you got 1 event. So you are randomly picking a unit area, and every time you are getting 1 dot. So it means events are independent, but it is not random. So there is no randomness associated, even though the rate of average occurrence is constant, but there is no random associated. Then this could not be considered as a Poisson process. Let's say if you have such a situation in which these dots are representing events, and you will find the cluster of events at different spaces which are randomly distributed. So here you select a random unit area, so you just select a unit area and then you find only one event. And let's say if you select another area and then you don't have any dots or any event. Let's say you select another unit area and this time you came across with 14 events or 14 dots. So this time you got 0 dots. So it means it is random, but the average number of occurrences. So even though it is independent, and what happens in the event is in this each trial is independent, but it is, this process is random as well. Sometimes you're getting different numbers, every time you're getting different numbers, but it is not satisfying the second condition. The average rate of occurrence is not constant, so it would not be considered as a Poisson process. So these are not the Poisson process, whether it is a pattern or whether it is a cluster. But if it is randomly placed dot, then it would be considered as a Poisson process. Okay, just take a problem and read this. Average weight of a customer arriving in a store in 10-minute period. And keep in mind, I'm talking about only 10-minute period. And let X is the weight of the customer arriving in the 10-minute period. So the question is X a Poisson variable? So take it a pause and try to answer this question, because if it is a Poisson variable, then it must be independent, as well as the rate of occurrence should be constant. For example, in a superstore, customers are arriving, and this is a very short period. You might come across with in a 10-minute period, might be 15 people has come in. 15 people have come in, and their average weight would be, some would be very heavy, some would be less heavy. So it could be distributed, it is a random process. There is no doubt that it would be a random process. But in that short period, the rate of occurrence, number of customers having average weight, is how it is distributed. It would not be considered as constant. Since this rate of occurrence is not constant, it would not be considered as a Poisson random variable. Consider this problem 2, in which the number of fatal airline crashes in a year. So different airlines operate in a year, and the number of airlines having the fatal crash, it means there are the whole plane crashes, and most of the people died in that event. So such an event would be considered as a fatal event. So let's say C is the number of crashes in a year. So if we observe the whole year, and in that period of time, the number of crashes could be, fatal crashes could be 4, could be 5, could be 6, could be 0. So, but it cannot be 100, it cannot be 200, or it cannot be 1000. So, I mean, try to answer this question whether it is satisfying both conditions. If it is satisfying both conditions, for example, the events are independent from year to year. Number of crashes has what happened in 2017 has nothing to do with what happened in 2018. And at the same time is a random process, and the rate of average occurrence is nearly constant. It does not change appreciably. Then this variable C would be considered as a Poisson random variable. Okay, try to answer this question. Take a pause. The number of fatalities in a commercial airline crashes in a year. So we are not talking about any number of airline, but we are talking about a particular commercial airline crashes in a year. For example, this number for a particular airline, then the number of fatalities would be number of deaths in airline crashes would be, for example, even one plane crashes and there are 200 people on board. So the number could be 250, or if it is a very small plane for that particular airline in a year, and then only, let's say, having 20 passengers, only 20 dies. or if no accident happens, so 0 died. So this number is a random variable and it is independent, but the rate of occurrence is not constant, because it can take any big number, it can take any small number. So that's why in this situation, for a particular airliner, it cannot be considered as a Poisson random variable. And you need to understand the difference between the problem 2 and 3. In problem 2, you're interested in the number of fatal airline crashes. So you whole world, how many fatal airline crashes occurs. So that number is not drastically changing. So it is average rate of occurrence is constant. But for a particular airline, this number can be drastically changed from year to year. So that's why it is not considered as a Poisson random variable. So you need to look very closely, finding out which variable is a Poisson random variable. Okay, now we are interested in deriving the probability mass function. Actually, we already know that probability mass function is a mathematical function, and for a given random variable, which is, if it is random variable is a discrete random variable, then you put that value of the random variable in that mathematical function and you get certain probability. And we know the criteria for a probability mass function is that the probability number would, for a given random variable, would be lying between 0 and 1, and sum of all the probabilities must be, if you add them together, it must be leading to 1. So let's say if x is your random variable, which is a binomially distributed, and the number of trials are fixed, and p is the probability of success, and the corresponding mathematical function which gives you the probability out of the finite number of trials, and when your trials are independent and meeting all those 4 conditions for binomial random variable. So this mathematical function is giving us the corresponding probability, and we use that capital X is representing a random variable which can take any value, and small x is the particular value of that random variable, and p of x is representing the corresponding probability. Consider a case we don't know the number of trials. So number of trials are not known, and the probability of success is remains the same as p. But what we know is the number of successes per unit period or per unit of space, and that average number of occurrence is represented by a letter lambda. So what I do is, if x is a random variable and if I have to take average of that random variable, so this would be the expected value of this binomial random variable, and we know the expected value can be easily calculated if you know the number of trials, and p is the probability of success, so your lambda would be equal to the product of n times p. Or if let's say you want to calculate probability, then probability would be lambda over n. And this is something, the probability in a random variable which is having a binomial probability mass function. This is not PDF, binomial probability mass function, because PDF we use a term for continuous distribution. For discrete distribution we use a term called probability mass function. So let's say in this particular distribution, which is a discrete binomial distribution, I put n and x, and instead of p, I just substitute lambda by n, and x is the value of that random variable, and 1 minus p would be, if this is p, then 1 minus p would be this thing. So I just have substituted the value of x, a random variable is the small x, and number of trials is n, and lambda is the average number of successes. So take the limit n goes to infinity. Let's say in the problem we have found in this binomial distribution is the number of trials must be finite. Let's say if we take a scenario in which n is not unknown and it could be a large number, let's say. So the whole probability mass function can be written in this form, where n is approaching towards infinity. So this whole probability mass function just have taken a limit for n approaches infinity. And now what actually I have done is just rewriting again the same thing, and then if you take it a common, lambda to the power x and x factorial. So because this term doesn't have the value of n, because here the limits are n, so we can take out of the limits and we can write as lambda, same thing to be written as lambda to the power x and x factorial. So taking it common, deliberately taking it common. So if you multiply it together, you are going to get the same thing. Okay, here you got it n factorial and x factorial you have taken common, and you have taken lambda to the power x common. So 1 upon n to the power x is already there, and this thing can be separated in two parts, 1 minus lambda to the power n having a power n as well as minus x. So if bases are same, if you add their powers, it would be the same, n minus x power. Okay, then what I need is to simplify this term, that is n factorial n minus x factorial over 1 over nx. So now all my attention, we will go back again to this equation and just focusing on simplifying this expression. So as you know, n factorial definition would be n minus 1, n minus 2, and it would be n minus x factorial over 1 over nx. And if you n minus x factorial and n minus x factorial can be cancelled out, so you end up with this thing. And since we cancelled out n minus x terms, the numerator here is left with x terms from n to n minus x plus 1. So this has x terms in the numerator and x terms in the denominator. Since n is to the power of x, so we can write like this, n over n, because it is going up to the power x. So n minus 1 over n, n minus 2 over n, and so on. So this term would be n minus x over n. So if all these are going in the x terms, so n1, n2, n1, 1, 1, 1, if you add them, it would be n to the power x. So this denominator can be split into this form. Okay, and here what I have done is n over n is 1, and n minus 1 over n can be written as by dividing n and n cancel out 1 minus 1 over n, and the same thing done on this term as well. Okay, at this place, you know, we put back this in our equation where we have a limit for that. We already have taken common lambda to the power over x factorial, and this term is simplified by bringing all these terms here. So the whole thing can be simplified using this simplified version. So n factorial n minus x factorial over 1 over nx can be represented in this square bracket. And the rest remains the same. And then what I did is I just colored three different terms, the blue term and the red term and the green term, because limit is being applied to these, all are the multipliers. So limit is applied to all these multipliers, and this is taking common. So I am separately dealing all these three terms having the limit. So the limit is all these are multipliers, so limit is applied to this term, limit is applied to this term, and limit is applied to this term, and I have given a particular color for each term. So first I deal with the blue term. So let's say I am interested in only this term. So first examine what can we simplify this term. What we done is apply the limits. When n approaches infinity, 1 upon infinity, 2 upon infinity. So as you know, 1 upon infinity is a very large number. So 1 upon infinity end up with 0. So you end up with 1. So its limiting case for this term would be equal to 1. So this term is quite, the left hand side is, this blue term is quite simple to evaluate. Okay, now we are focusing on this green term. Lambda n approaches infinity, 1 minus lambda over n to the power minus x. Okay, so once you apply the limit, as you know, n approaches infinity, so here 1 upon infinity would be 0, and 1 to the power any power would be 1. So by applying these limits, you will end up with simplifying the blue term and the green term. Now you only end up with the red term. Okay, now look for the red term. Red term is complicated because here once you put n approaches infinity and having some power infinity, then this would not be this would be 0, but 1 to the power infinity is not it is an indeterminate case. Okay, in order to deal with the indeterminate case, we take an algebraic trick by just taking 1 minus lambda over n equal to y and taking a natural log on both sides. And then we use the property of log, and n is brought on this side, and then we can write ln y should be equal to ln, and this n can be written as 1 upon n, because if you go up it will be exactly the same as n. And then I take limits on both sides, because my limits is n approaches infinity, and this time also I got an indeterminate case. Now what I need is to get rid of this indeterminate form. I need to apply the L'Hopital rule, which by differentiating numerator as well as denominator. So if you differentiate ln of x, it would be 1 upon x and derivative of x. So the derivative of x would be minus lambda over n square, and similarly the derivative of 1 upon n would be minus 1 upon n square. And if you simplify this, you got again an indeterminate form. And here if you look at this, again further applying the L'Hopital rule, then n derivative of n lambda would be lambda, and here it would be minus 1, and minus 1 cancels out with respect to n. So derivative is n. Lambda is a constant, so here the derivative is 1, and here the derivative is minus lambda. So this term comes out to be, the whole thing comes out to be minus lambda. I replace back to that equation, and then got this blue limit, red limit actually. So this limit comes out to, because log of this is limit, log of something is this, then limit of this thing would be e to the power minus lambda. Okay, now I substitute every term in that our expression. So each color is this one is already 1, and the green one is 1, and the whole red one is e to the power minus lambda. Okay, I got it. Then this would be my probability mass function for an exponential distribution, which we can think of a special case. Poisson distribution is nothing, a special case of a binomial distribution when n is large and the probability of success is low. Because probability n could be, how can be n could be large when probability is lambda by n. So if n is large, then probability comes out to be a small value. So that is the case of a rare event where probability is low. So formally we can say that the probability mass function of a Poisson random variable with a single, and in this equation, in this function, the parameter is only a lambda. So this is a single parameter distribution. So we can say x is a random variable, and the value of the random variable is small x, and the corresponding probability is represented by this mathematical function e to the power minus lambda, lambda to the power x over x factorial, and x can take only discrete values, because here capital X is a discrete random variable. So we can shortly represent that random variable with Poisson. PO represent the Poisson distribution with a single parameter lambda, which is actually the average rate of occurrence. So if you know the average rate of occurrence, you can easily calculate its corresponding probability. And you have all these different notations to represent the corresponding probability. It is, these two notations you are already familiar, and sometimes you will write P for probability. This capital X is representing that X is a discrete random variable. So sometimes people write. So let's see how we apply the Poisson distribution, probability mass function of the Poisson distribution to solve this problem. So you have a nanogram of plutonium-39 which have an average 2.3 radioactive decays per second. So it is actually the number of occurrence in an event is every second 2.3 radioactive decays, and the number of decays will follow a Poisson distribution. So it has been already mentioned that this random variable number of decays could be any number following the Poisson distribution. So what you need to find out the probability that in 2 second period there are exactly three radioactive decays. So here average rate of decay per second is given. So for first of all we have to calculate the random variable x. Here would be the number of decays in 2 seconds, because we have to calculate number of exactly three radioactive decays in a 2 second period. So we are assuming it that let's x be a random variable and the number of decays in 2 second period would be a random variable, and this random variable is Poisson, has a Poisson distribution, and the parameter of the Poisson distribution here is the average rate of occurrence. So we have to calculate the average rate of occurrence for exactly three radioactive decays per 2 second period. As you have seen in the problem, the radioactive decay rate is for per second is given. So if 1 second it is through 2.3 is the number of radioactive decays, then in 2 second period it would be 2.3 multiplied by 2, so that would be 4.6. so average number of decay rate would be 4.6. so lambda parameter would be 4.6 here. And now just substitute in the probability mass function to calculate the corresponding probability when the value of x is equal to 3, and just substitute e to the power minus lambda and lambda to the power x over x factorial. So 16.3% is the probability that exactly three radioactive decays happens in 2 second period. If we see the distribution we have calculated for x equal to 3, we got that number 0.163, something like that, 0.163 when x equal to 3. So some number you will get when x equals to 2, some number you will get x equals to 4, then average is 4.6. so the central tendency of the data is over 4.6. so as the x increases, the probability of finding more number of decays is having a low probability. So this distribution gives us the typical distribution, probability distribution, and the mathematical function to calculate the probability would be the probability mass function for every value of the random variable. A random variable can take numbers 0, 1, 2, 3, and these numbers would be the discrete numbers. Let's see another problem. You have a complex software system where every 5,000 line of code average errors are 7 number of errors. We have to calculate in part A the probability of exactly getting 2 errors in 5,000 line of code. So this problem is simple because the error number of errors in 5,000 line of code would be a random variable x, and just we are assuming that it follows a Poisson distribution, and every 5,000 lines of code average number of errors would be 7 errors. So here the lambda would be 7, and we have to calculate for x equal to 2 number of errors the probability, then substitute x equals to 2 in the probability mass function e to the power minus lambda. Lambda here is 7 and lambda to the power x over x factorial. So you got a probability of 2.234% is the probability that in 5,000 lines of code you are exactly getting 2 errors. Let's say in part B you are required to find the probability that at least 2 errors means the error would be greater than 2, 3, 4, 5, 6. So we calculate by other way around. Probability x is greater than 2 means 1 minus probability x less than 2. Less than 2 means it could be 1, x1, it could be x0. So just calculate the probability at x equal to 0 by substituting x0 and probability x equal to 1 by substituting 1, and to calculate. So 99.275% is the probability that you are going to get at least 2 errors. So it would be 2, it would be 3, it would be 4. So this is how you have calculated. Okay, we just have another problem. Let's say a software system averages 7 errors per 5,000 line of code. So here the lines of code is 5,000, and you have to calculate the probability for exactly 3 errors, not for 5,000 lines of code but for 15,000 lines of code. So here you need to be careful about the parameter lambda, because here lambda is you need to calculate for 15,000 lines of code. So for every 5,000 line of code you have every 7 error. So 7 per 5,000 lines multiplied by 15,000 lines, it would be average would be For 15,000 line of code, the average would be not 7 but average would be 21. So here the parameter random variable would be taken as 21 and substitute the value for x equals to 3. So there is a very small probability, 0.0012% is the probability, or just 0.00012% is the probability that out of 15,000 lines of code you are getting exactly 3 errors. So this is how we solve the problem related with Poisson distributions. In the next lecture we will see it how to do the same thing on Minitab as well. I stop this lecture.